So welcome to this new video entitled Embedded Processors. In this new video, we will study the different categories of processors that are embedded, and we will give an overview of the common families that are used in recent FPGA devices from Xilinx and Intel in particular. So in fact, there are three types of embedded processors that can be available in an FPGA. The first one is called a hardcore processor. This type of processor is completely separated from the reconfigurable FPGA fabric, meaning that it is entirely implemented in silicon and is already provided when you buy the chip, actually. The other type of embedded processor is a soft core. This type of processor can be implemented within the FPGA fabric, meaning that it is made of logic cells or logic blocks and not directly implemented in silicon. In this case, designers have the flexibility to choose the processor's instruction set, the hardware features, the memory and peripherals that are associated with the processor. They may also choose data and address sites in memory. The soft core can be seen as an IP that is made available by vendors, either Xilinx or Intel, and such processors often come with a bunch of libraries and assembly tools or compilers, linkers that can be directly used to manage this processor. The third type of embedded processor within an FPGA is what we call a custom design. It means that it's up to designers to build their own processor core that they can describe in VHDL, in Verilog, or using any hardware description language. They are also responsible for providing all the tools that are going to be necessary to program this core. This table here shows the different features, advantages and drawbacks of the different processor types within an FPGA. For example, if you take a look at the hardcore, we can see that the key features are a fixed architecture and that is designed for a specific application. One of the main advantages is that this type of processor does not rely on the FPGA fabric, so designers have the possibility to use the reconfigurable areas for something else. The other important thing is that these processors are faster than their counterparts because they are optimized since they are designed in silicon and can run very high in terms of frequency. The main drawback of this type of architecture is that it's fixed and not really flexible. The other important disadvantage is that you can't discard extra unused features. For example, if a programmer doesn't want to use a specific part of the processor, it's still implemented in the FPGA, and there's a waste of resource in this case. Regarding the soft core, the key features are the customization of instructions, of hardware features, data addresses, and size, so everything can be modified by the end user, which is very interesting. In fact, designers may instantiate a core whenever it's needed. They can even instantiate several of these cores. Today, we can implement up to tens of these cores without any problem in a single chip. In general, they are much more simpler than the hardcore counterparts, and a given microprocessor is usually developed for specific application and performance needs. So we can configure the soft core to make sure that it's compatible with the application constraints. The main disadvantage of this type of architecture is that it's much slower than the hardcores. The third type of processor is the HDL processor core. For this type of core, designers develop a custom project to suit the application needs. So they're able to build a processor from scratch and optimize it for better power and resource utilization. In this case, there's no waste of resources since the processor is completely tightened to the designer's constraints. The drawbacks of these processors are the lack of availability of tools like compilers or other development tools. In fact, it's up to designers to provide these tools once they build the processor, which is a huge task and something that designers usually want to avoid because it's really time consuming and that it requires a lot of people to develop this kind of tools. The same idea is also a lack of support when developing and testing the HDL code of the processor. So the next slide, this slide here, shows what's inside an SOPC with a hard core. So you can see in the middle of the chip some black rectangle which corresponds to a processor core. This is a quite old circuit from Xilinx. I think it corresponds to the Vertex 2 Pro device. What is interesting here is to see the size of the hard core compared to the FPGA fabric. And you can notice here that it's not negligible at all. What you see here in blue are all the connections that are implemented and routed within the FPGA fabric to make the processor communicate with different peripherals that have been implemented on the reconfigurable regions. We can also distinguish some of the logic cells that are positioned within a matrix, and you may also see that the black rectangles here are related to the block RAM memory in the FPGA. So if we take a look at the research costs of several technologies, we may say that ASICs are much more expensive. For example, total costs including research, development cost, test, used to reach something like $20 million for a standard 130 nanometer CMOS technology, which is a very old one. For a 65 nanometer, it's $50 million that were required to build a single chip. Furthermore, the time delay is also high, and it's the order is something like 18 months. So for FPGA, this total cost is not comparable, since a 10K gate device only costs something like $1. So before continuing the description of the different processors, I'd like to talk about interconnections, because this is something that is very, very important in FPGA, and that allows designers to connect the different processors with the available peripherals. As you may see here, there are different types of interconnections that are available within a chip. Today, the most common is the bus. If we go back to the 90s, the communication between different elements was ensured by point-to-point connections without any global standard. Then some shared bus standards have been introduced. Note that we call share the bus is simply a way to connect different peripherals or cores on the same wires. In this case, a protocol is required to make sure that the communication is well established between the different components and that there are no conflict during communication. After these shared buses, hierarchical buses have been introduced. These are composed of different types of buses. For example, one bus can be highly efficient since it's close to the processor and its memory. In this case, we can make sure that the communication is very fast. Then you can have other buses with less performance that can be used to connect different elements that are not very often used or that do not require to communicate intensively with the processor. In this case, bridges are required to make the link between the different buses and to make sure that the different standards can understand each other, can communicate with each other. Finally, the third type of interconnection is called a bus matrix, also called a crossbar, which makes it possible to connect different elements with each other. The problem in this kind of communication medium is that it takes a lot of resources within the FPGA fabric. Finally, one of the most famous communication medium in an FPGA is called a network on chip, meaning that it is possible to reproduce some network within the FPGA fabric. In these networks, you can find routers and other elements that are used to manage the network. These networks are very powerful but much difficult to implement because of their complexity. Nevertheless, this seems to be the trend in the future, to make multiple cores within a chip communicate with each other. Today we talk about hundreds, even thousands of cores within a chip, and this is very important to find an efficient way to make them communicate with each other. So I just want to give some words and terminology to make sure that we speak the same language. And so let's start with the first definition, which is the bus. The bus can be seen as a set of wires, okay, that are shared by multiple component elements with logic to control its use. Then, associated with this bus, which is just a physical structure, you have a protocol. A bus protocol is a set of rules for transmitting information between two or more components over a bus. So you can find sequences of events, timing information, protocol data, etc., etc. Everything is well defined. Then you have the master. A master is an IP initiating a data transfer, meaning that it can write or read data to or from what is called a slave. A slave is an IP responding only to the request of the master. An arbiter, then, is another element which is very important in the bus. It is required to control and manage the bus success in case where you have multiple modules that want to communicate with each other. A decoder is in general implemented within a peripheral or a device, and it determines which receiver has to be taken into account for the transfer. In other words, it is able to recognize which block is sending data. As we mentioned earlier, a bridge is a device that connects two buses which are not of the same type, having different protocols, and this bridge acts as a master on one side and as a slave on the other. So a bus may have different signals. The first signal is an address. The address bus carries the address of destination for which the transfer is initiated. It's always configured as a write bus. The data signals, or data bus, carry information between a source and a destination, and this data bus is in general accessible in both read and write modes. Finally, there's another bus, which is called a control bus, that is used to carry requests and acknowledgement, and is also used to transmit other signals like enable, data size, and any other control signal that can be used by the peripherals. These buses are usually also available in both read and write modes. Before continuing, I would like to say just a few words about the shared system bus, since it's the type of bus that we're going to consider in the next lectures and also in the lab. A shared bus is made out of simple wires that are used as a shared communication medium, interconnecting several modules. Only one module can access the bus at a given time, which is something really important to avoid conflict. It means that it requires an arbiter to manage internal communication. In this type of system, all devices are usually memory mapped, meaning that all transactions use a target address within the processor's memory space. We'll talk about that in more detail a little bit later. You can also find streaming communication. In streaming mode, the peripherals or the IPs are not connected to the bus and communicate through dedicated components called FIFOs without any address requirements. Okay? So in the following now, I will give examples of embedded processors starting with the Xilinx family. We'll start with the Microblaze, which is very popular but a little bit old, which can be used in a lot of FPGA today, even the smallest, and the microblaze is a soft core. Then I will describe the zinc device, which is a hard core that is much more recent and much more efficient, but also very complex, as you will see. So let's start with the microblaze. The microblaze processor is an embedded RISC processor. Remember that RISC stands for Reduced Instruction Set Processor. It is a 32-bit processor, meaning that it can work on data which are coded into 32 bits. It also considers 32-bit instruction words with 3 operands and 2 addressing modes. It's a small architecture that is composed of 32 registers that are 32-bit wide each. And this processor features 3 pipeline stages, and it's working on either little or big Indian format. Regarding buses, it contains a full Harvard architecture. If you recall what is an Harvard architecture, it means that the data bus and the instruction bus are completely isolated from each other for much efficiency. It also features an OPB Core Connect standard bus from IBM and an LMB for connecting to local BRAMs, which is much more efficient to transfer instruction and data. So here we see the microblaze architecture, which is very simple. You see here the arithmetic and logic unit, which is closely tightened to the register file here, made out of 32 registers. Like any other processor, you have a program counter, which is a counter that points to the next instruction to be executed. In addition, you have an instruction side bus interface and a data side bus interface to communicate with the external world. So you see here that the processor itself is really simple. This processor is available in a library where you can customize it to your very needs. One of the interesting things in such cores is that you can modify the instruction set. That is to say that it's possible for designers to add some instructions to the processor. This is very powerful. For example, you can plug a hardware accelerator. In this example on this slide, it's an FFT, a fast Fourier transform. You can modify the instruction set of the processor to integrate this FFT as an instruction that can be directly called from software. This is very powerful because it's completely transparent to the final users. You can simply call a specific instruction in your program to perform a complex computation without considering very complex design steps and without considering the way the microblaze and the IP, the FFT, are communicating. In this example, we see that the microblaze and the FFT communicate through FSLs, which are sort of FIFO buffers to exchange data. This communication is automatically managed by the Xilinx tools, so you don't need to worry about that. So in this table, we'll show the microblaze performances when it's implemented on various devices. When implemented in a very small FPGA, like a Spartan 2, its speed is quite small since it features like 65 MHz clock frequency and the performance is only 43 DMIPS. It can also run much faster in other types of FPGAs. For example, in Vertex 2, you can reach 150 MHz as clock frequency. The logic cells column is here to present the amount of resources that is required to implement the processor. For example, a simple processor like a microblaze can use about 1000 logic cells of the FPGA. So if you have a global idea of the number of logic cells that are available in the device, then you can easily imagine the number of processors that can be implemented within this very device. So it can be something like 10 or even more. It really depends on the device that you have. The table below shows the performance of a microblaze on various types of more recent FPGA devices like the Zinc 7000, the Vertex 7 FPGA, Kintex 7, etc., etc. So this slide shows the microblaze configuration and how it communicates with the different peripherals that are implemented within the FPGA fabric. For example, we see that the microblaze can communicate with a 32-bit bus with a BRAM for the most performance. There's also an additional OPB bus that is used to make the microblaze communicate either with the external memory or other devices like GPIOs, Ethernet, LCDs, other memories, or the UART interface. We will see later that this communication between the microblaze and the different peripherals is completely automated, meaning that designers don't have to worry about the way that devices communicate with each other. Everything is already provided by the vendor, and it's very easy to build this type of system. So here's an example of the Zinc processing device, which is very popular. It's implemented in lots of Xilinx FPGAs today. It's a complete ARM-based processing system which features dual ARM Cortex-A9 cores. It integrates memory controllers and peripherals and is fully autonomous to the programmable logic. What makes it very powerful is that it's tightly connected to the programmable logic. The fabric is used here to extend the processing system and can be seen as an accelerator. This is made possible by high-performance interfaces. One thing that is also very interesting is the flexible array of input-outputs. You can have a wide range of external multi-standard input-outputs that are compatible with all standards and that can make it possible to communicate with a lot of various devices. There are also high-performance integrated serial transceivers that can reach up to several gigahertz to transfer tens of gigabits. Finally, we can also find analog to digital converter inputs. This is very useful if you want to connect your device to some specific sensors, for example. It can be used for edge computing to perform computation very close to where you get data from sensors. So this can be very useful. So here's an overview of the Zinc processing system, which is the Zinc 7000 SoC. Here you see in green the application processor unit, which constitutes the core of the system. This core is based on two ARM Cortex-A9 CPUs here. Associated with the CPUs, there are a memory management unit, MMU, a floating point unit, FPU, and a neon engine for process acceleration. Everything is in the APU. You also have additional peripheral close to the processors like timers here, DMA channels, whatever. The central interconnect is used to connect all the various elements with the processing system and with the different I/O peripherals with general purpose ports, and make sure you have a very performing communication between the processor and the programmable logic, which is implemented in the FPGA. Okay. This shows the Zinc memory map, just to show how it interfaces with the peripherals. The Cortex-A9 processors uses 32-bit addressing, and all peripherals, system peripherals, but also the peripherals that are embedded in the programmable logic, are memory mapped to the Cortex-A9 cores. For example, all slave PL peripherals are located within these two addresses between this one and this one. Okay, and this constitutes the first section. There's another section between 8000 and this BFFFFF. The other addresses are used to access specific devices within the PS part, like specific registers, memories, or internal peripherals. The list is available here in this table. This slide shows just an example of a very recent device by Xilinx. It's just to show that recent SOPC have become very complex in their structure, which will have consequences in terms of design. These devices example feature heterogeneous processing system composed of a dual Cortex A53 cores and a dual-core Cortex R5 real-time processing unit. Mated with 16 nanometer FinFET programmable logic, these devices are optimized for industrial motor control, sensor fusion, industrial IoT application, and a lot of applications. These devices deliver exceptional performance per watt, which makes them very good candidates for a lot of application. Okay, so we have studied the Xilinx products so far. Now we're going to look at the Intel devices, which you will see are quite similar to the devices that have been previously shown. I'll start with the ARM Cortex A53 core, which is the most recent device implemented in the Stratix FPGA from Intel. Then I talk about the ARM Cortex A9 hardcore, which is used in other Intel products. Finally, we will describe in detail the Nios 2 processor, which is the famous one, and which is the soft core that we're going to use in the lab associated with this course. So let's start with the Intel Stratix 10 SoC. These devices are manufactured on Intel 14 nanometer FinFET process. They are very powerful devices, in fact the most complex of Intel FPGAs, and are used in a high demanding application. They feature a hard processor system called HPS, based on a quad-core ARM Cortex A53 cluster. The HPS also includes a lot of peripherals. All these elements make use of the new technology, Intel HyperFlex FPGA architecture, and this architecture introduces additional bypassable registers everywhere throughout the FPGA fabric. These additional registers, called hyper registers, are available on every interconnect routing segment and at the inputs of all functional blocks. This significantly increases the level of performance in terms of speed, but also logic density. The other type of embedded processors to be found in Intel is the ARM Cortex A9. These processors are usually implemented in smaller devices, but still can reach high performance and flexibility. The slide here shows the example of the Intel Aria device, which belongs to a family of rather small devices. It consists of an HPS that is composed of a dual-core ARM Cortex A9 coupled with additional peripherals. So I don't want to go too deep in the architecture. You will have much more information on the Intel website. I just wanted to point out that either Xilinx or Intel technologies are rather similar, and that they are composed of the same cores coming from ARM. It is then important for you to understand the ARM architecture, obviously, but also understand the interactions with the programmable logic. And this is what we're going to study in the next lectures. For now, thank you very much for watching this video, and feel free to contact me if you have any questions.